We're about to start with Pam Knox. She is a climate specialist in the University of Georgia's Department of Crop and Soil Sciences. She has worked for over 30 years in applied climatology and is also a certified consulting meteorologist working in forensic meteorology. She has previously worked with the Georgia Assistant State Climatologist and the Wisconsin State Climatologist, as well as for the National Weather Service in their Office of Hydrology. Today, Pam will be talking to us about climate vulnerabilities and forecasting in the Southeast. And with that, I'm going to hand it over to Pam.
Great, thank you, Dan. Good morning, everyone. My name is Pam Knox, as Dan mentioned, and I'm with the UGA. I'm a climatologist. I've been doing it for about 30 years now. And it's my job this morning to set the stage for the rest of the talks today and tomorrow by talking about climate in the Southeast and both present climate and future climate. So we're going to jump right in here, see if I can get this going. There we go. What I'm going to basically talk about are three things. First of all, the general climate conditions that we're experiencing now, because I think most people like to know that and looking at short-term things. I'm also going to look at long-term climate trends over the last 100 years and what some of those things might mean for the future. And then finally talk about some of the impacts of changing climate on working lands. Just want to briefly mention that climate is controlled by a number of factors, some of which we can control and many of which we cannot. Climate is controlled by the physical geography of any particular location. That includes things like the latitude, which affects the amount of solar radiation we get, elevation, the presence of water, and land cover. Of course, land cover is something that we do change over time, and it's probably one of the factors that has affected temperature trends in the Southeast over the last 100 years. Other things that can vary naturally are things like the water vapor in the atmosphere, aerosols, and those could be both natural aerosols like volcanic activity or aerosols from air pollution. Also, other things like Steve mentioned, carbon dioxide and other gases such as methane. Some of those are naturally occurring, some of them are human-induced, and some of them are a combination of both, which makes it a little tricky to deal with when you're trying to do predictions of the future. Since we're talking about vulnerability, I thought it'd be worth it to just mention for a minute some of the vulnerabilities that we have here in the Southeast to weather and climate. Of course, extreme heat, nobody's really thinking about today because it's pretty cold outside, but it certainly can stress humans, animals, and plants across the Southeast. Extreme cold, which probably you're more thinking about today, can cause frost damage to plants. That could ultimately reduce yield. We're looking at that this year for blueberries because the warm December started blooming in some of the early varieties of blueberries down in southern Georgia, and those have all frozen off now and will probably reduce yields later this spring. Another vulnerability, of course, is to drought, one of the big ones that I talk about a lot. Drought can cause loss of yield or sometimes a loss of the total crop and can reduce water supplies and cause damage to ecosystems as well. The other side of that is floods, and floods can cause a lot of the same damage, but of course for different reasons. Can destroy infrastructure, wash away crops, and cause loss of life. Also affects the health of plants by suffocating the plant's roots. And then finally on this list here, severe weather can do damage to infrastructure or can damage crops. When we're talking about crops, it can be hail, and it doesn't really even have to be big hail to be an important factor, because if it changes the cosmetic appearance of the crops, that can cause a loss of value. I just want to start by talking about 2015. This is a map of the temperature departure from normal for 2015 across the Southeast. And if you look at this carefully, you can see almost everywhere in the Southeast it was above normal in 2015. Some of the places that were the brightest red are the highest departure from normal. And Florida really kind of stands out there as the area with the most bright red, although Southeast Alabama also has an area. You might think a difference from normal of a couple degrees wouldn't be a big deal, but it actually turns out that for Florida, they set their record highest temperature ever in 121 years of record for 2015. Most of the Southeast was well above normal, but not necessarily the record setting. So we're starting off in a year that's been quite a bit warmer than normal, although obviously there's been some variations. This is a map of the precipitation departure from normal. This is taken from radar analysis, and again, it's as a departure from normal rather than the raw numbers. You can see the scale on the right-hand side here shows the values in greens and up to pinks are above normal, while the color range in the yellows and reds are below normal. And there's quite a range across the southeast. There's this whole swath from South Carolina that goes into northern Georgia. That's where they had all the heavy rains in the beginning part of October. That has really affected their yearly totals. But the southeast also has had areas that have been fairly dry. The area in southern Georgia and northern Florida has been quite dry, and they've had some lingering abnormally dry conditions. I think the drought is all gone right now from there, but it's still dry and could go back into drought conditions if they don't get rain in the near future. Of course, the really big departures from normal are Texas and Oklahoma, and you can see that Texas and Oklahoma in the small inset graph here actually set records for the wettest year on record. And so it's really been amazing. Most of the U.S. has been above normal in precipitation as well as above normal in temperature, and that's really odd. It's very unusual to have both of them, because usually when you have a lot of rainfall, it keeps the sun down and keeps the temperatures down. So that's something that's been very interesting to look at this year. Just for an example of how things vary, this is a thermograph for Atlanta. I just picked this out sort of in the middle of the southeast. And you can see the green here is the band of the normal daily highs and lows, and the grays that are superimposed on it are the actual values for 2015. The reds and the blues show the extremes for each particular date. You can see there's, as expected, a lot of variability through the year. We had cold spells in February, and also a little bit in the summer, especially if you look at late April and then late June, there were some cold spells. And then really the thing that sticks out the most is what happened in December, where the temperatures were way above normal. We had record-setting temperatures on several days in a row. And if you actually look across, those are normal temperatures that are more like September rather than December. And so it fooled a lot of the plants into thinking it was time to grow, and it will probably cause some issues in this coming growing season. You can also see the amount of rainfall in Atlanta in that band of wet conditions was well above normal conditions. So that kind of gives you a blueprint. Notice in the growing season, the summer, temperatures weren't record-setting by any stretch of the imagination, but they were pretty consistently above normal over the long haul. Another thing that I like to look at is the distribution of drought in the southeast over time. This particular product started in 2000. You can see at that time the southeast was already in a drought. That had started in 1998, and it continued until really the end of 2002. That drought was focused especially on Alabama and Georgia. The second drought, which in Georgia at least was the worst, was 2007 to 2009, which focused on northern Georgia, caused a lot of problems for water supplies here in Athens, and also some questions about water supplies in Atlanta. The governor had a prayer conference to pray for rain, which he very carefully picked on a day when rain was forecast. And then we had a little bit of wet conditions, and we went back into the third drought in the last 20 years. In 2011 to 2012, that drought was mostly in southern Georgia and southern Alabama, and didn't really get a lot of attention by the media. You can see since that time we haven't had a lot of drought. There's a little blip here in late 2014. That was mostly centered in the Carolinas, North and South Carolina, and that was all wiped away by the floods in October. So that really has gone away. You know, if you look at this pattern, you might think, well, or maybe we're about due for another drought, and I'm going to talk about that a little bit in a few minutes. So some of the impacts of the recent climate on the southeast have been these repeated episodes of drought have caused a lot of stress on the trees. And so we've had a lot of problems with tree falls and trees dying. I've had 4 trees go down in my own yard at home, some of which were probably related to the life of the tree, but certainly some of them were also related to weather and the drought. Lower groundwater levels overall, because those droughts, especially at the deeper aquifers, just can't really resupply the water there. The recent wet periods have caused tree falls as well, because it destroys the strength of the roots and the soil that's supporting those roots. And so that's a problem. It can also cause significant flooding, as you know. And then the very warm weather in December, as I mentioned, has led to unusual plant growth, making it vulnerable to cold weather and frost in the spring. So that's kind of where we're at right now. Waiting for my arrows to come back. There we go. We take a look at the longer-term trends in temperature. This is the annual average temperature for the Southeast, starting in 1895 on the left and going to 2015 on the right. And you can see the year-to-year variability of that quite well in the purple. And then I've drawn, just for simplicity, a little trend line here in red. Obviously the trend line it shows some things about what's going on with the temperature, but there's a lot of variation that isn't really caught by a single trend line. For example, if you look early in the period, there's this fairly rapid rise from 1895 to about 1950 or so, then a pretty dramatic decrease in temperatures from about 1950 to 1970. And since that time, another fairly rapid increase in temperatures. And it turns out that that rapid increase in temperatures is pretty consistent with what's been going on in other parts of the world, and certainly other parts of the U.S., but it's not necessarily something that we've seen. We haven't seen that consistency between the Southeast and the rest of the world in other periods, and so that's something we're going to discuss in just a minute. And just for curiosity, I'd also like to show the time series for a much shorter time period. You can see here, this is 1998 to 2014 or so. It's very close to a flat line. This is what they call the warming hiatus by some groups. It really depends more on cherry picking a really strong warm year to start the series with, rather than a long-term trend. You can see that's over a short period, but it does show up a lot in arguments about how global warming has ended, which I hear quite a bit from some of my more conservative folks that I talk to. And so trends are a tricky thing because they really depend on where you're starting your line and where you're ending your line. Short term, you can have trends that are different than the long-term trend, and it's important to look at all of those because, when you're managing at different time scales. If you're managing a crop, you're probably looking just a couple of years ahead. If you're managing livestock, you might be looking 5 to 10 years ahead, or maybe a little longer if you're worried about infrastructure changes like barns. And if you're managing a forest, you're probably looking 30 to 40 years down the road. And so the trend line is going to be different, and you're going to have to take those into account. Now, the Southeast is not like a lot of the rest of the U.S. This shows the trends over time as a series of colors. You can see the red here, which is really the western United States, and the northern United States has the biggest change over time. This is over the last 100 years, whereas here in the Southeast, we've been in what we call a warming hole. The trend has been very slight compared to what's happening in other places. And it's important to keep in mind when you're in the Southeast, if you talk to colleagues that are in Wisconsin or colleagues that are in the Northwest, they're going to have very different experiences than what we do have here in the Southeast. And if we would look at Alaska, the trends are even stronger because as you get closer to the poles, you have to worry more about the influences of snow or lack of snow. And so those trends are even worse. And there's no doubt in those places that the climate is changing, and they're seeing really big changes in their infrastructure and their temperatures and precipitation as well. So the Southeast has been kind of an anomaly overall. We think a lot of that probably has to do with land use changes. I mentioned that on the first slide as a way that humans can change what's going on in the environment and affect the climate. 100 years ago, there was a lot of bare soils and cotton cropping in the Southeast. With the boll weevil and the development of more irrigation out west, a lot of the cotton moved to the California section of the country, and so really they did less here in the Southeast, and a lot of the Southeast became reforested. I've heard statistics that say the Southeast is now more than 70% forested, and forests are generally cooler and a little moister than the bare soils of cotton fields are, and so that probably has helped to impact the trends in temperature over time in the Southeast. So there's lots of different ways that we can affect the climate. It doesn't just what we put into the atmosphere, but ways that we affect the ground as well. So this is a national temperature trend, again, from 1895 to the present. And here's the purple. You can see the upward trend for the national is stronger than it was for the U.S. For the Southeast. And so that's not surprising considering the map I just showed you. There's still this period from about 30 or 40 to about 70 where it was cooling down, scientists are starting to think that that's probably a combination of natural and man-made aerosols. In other words, there's some volcanic activity that was cooling things off, but that was also the period before the Clean Air Act, which came in 1970. So there was more and more industrial pollutants being put into the atmosphere, and that probably also reduced the amount of sunlight and energy that was coming in. So that's kind of an interesting thing, and that's really an area of active research that people are trying to understand why that decrease occurred from about the 40s to the 70s. If we look at precipitation instead, this is the U.S. map for precipitation. It shows that there is an increase in precipitation over the U.S. over time. It's interesting, this is also a little different than the Southeast, because in the Southeast, the trend is really very low for the annual average precipitation. It's the higher amounts of precipitation that are increasing tend to be in higher latitudes than what we're seeing in the Southeast. But there's definitely a slight upward trend in precipitation over the U.S. over time. And one of the things about precipitation, that's the annual average, but if you break it down by season, of course seasons are important to agricultural producers, especially farmers. You can see that if you break it down by seasons, spring, summer, and winter are actually getting drier for a lot of the Southeast over the last 100 years, whereas fall is getting wetter. Now that has some interesting implications for things like crop harvest, because fall is really when you want it to be dry, because you're trying to dry down your cotton, you're trying to get into the fields and do your harvest. You don't really want that rain. So that may in the long run cause some changes to the way that farmers have to manage their crops. Whereas in spring, summer, and winter, you know, they're looking forward to the planting season. They need to have soil moisture so they can get the plants to germinate. But again, they don't want too much because then it's hard to get into the fields. So it'll be interesting to see what happens with these changes over time. And these are all based on observations. They're not based on models. Here's another view of the national precipitation trends. The dot plot on the left-hand side here shows areas in red where precipitation trends are going upward, and the areas in blue are areas where precipitation is going downward over the last 100 years. You can see there's more variation with this than there is with temperature. There's areas like California where the precipitation is decreasing over time. That may in part reflect the fact that they've been in a drought for the last few years. Also, the northern plains seems to be getting drier, but many other areas of the country, including most of the East Coast, are getting wetter. And that's probably a good thing for agricultural production. If you break it down by extreme rainfalls, here we have in the lower right-hand side, by decades, the number of days of 2 inches or more in a 24-hour period, which we call heavy rains. The amount of heavy rains over the Southeast has increased by 27% in the last 100 years. So if you kind of do the math, you say, well, the average annual rainfall is not increasing in the Southeast, but the number of days with really heavy rain have increased. That means there's probably longer dry spells in between, and in fact, we really are seeing that. So that's going to be important because you have to have soil that's able to carry water holding capacity for plants, because they're going to have those longer dry spells. Now, the next thing you might want to consider is, well, how are we going to predict future climate? And there's a variety of ways to do that. Some people say, well, we're just not going to worry about any change and we'll deal with whatever happens. Easier to do if you're worried about looking a year or two ahead rather than looking 30 or 40 years down the road, because there is still going to be a lot of variability, and year-to-year variation, both in climate and in markets and things like that, are really going to drive a lot of the short-term trends. Another approach is to say, well, we've seen these trends, we're just going to assume that whatever trends are there are going to just continue at the same rate. And in fact, in some areas like North Carolina, looking at trends in sea level rise, they've put into law saying that when you design buildings along the coast, you have to assume that the trend is going to stay the same. You can't assume it's going to accelerate or anything like that. You have to assume that it's going to stay the same. Another way of looking at predicting future climate is to assume that we'll swing back to a former pattern. This is something that works better when you have really clearly identified things like El Nino, which I'll talk about in just a minute. Also works on an extremely long scale when you're talking about things like ice ages, but that's, you know, the scale of 10 to 100,000 years, so it's not something that's going to help us in management. So we'll talk about that a little bit. And then the fourth way of doing it is to do some sort of simulation or model of what the of what the climate might look like using computer simulations. And we're going to talk a little bit more about that too as the talk progresses here. When we look at some of the shorter term variations, the big one that comes to mind in the southeast is El Nino and La Nina. This is two opposite phases of the Pacific Ocean and the eastern equatorial Pacific Ocean. In an El Nino, the trade winds are weaker and it lets a lot of warm air build up right along the coast of Peru and Ecuador. That kind of acts like putting a rock into the river because this warm water builds up a lot of thunderstorms above it, and that can divert the atmosphere that's above it. And one of the things that happens is that in the southeast, in an El Nino year, we tend to have a lot of storms that come over us in the winter. And of course, we're certainly seeing that this year. The opposite phase is a La Nina, where the wind is really strong. Actually, the El Nino is on the bottom here, is on the top. The winds are really strong, so it piles all the warmest water in the western part of the Pacific Ocean. And so all the thunderstorms are there. And in La Nina winters here in the southeast, we tend to see warmer and drier conditions than usual. There's some impacts in the summer as well. I'll talk about that a little bit more in a minute. The biggest impacts are always seen in the winter, which is why it's called El Nino, because it was associated with the coming of the Christ child. And when climatologists look at the effects of these events like El Ninos or La Ninas, we tend to use a lot of statistical studies. We pick out the years with the strongest signals and we look at what the overall pattern was in temperature and precipitation. These are some graphs here that show that in an El Nino winter, the southern part of the United States, especially Florida and along the Gulf and Atlantic coast, the rainfall is quite a bit above normal, and that's very consistent. There is some variation from one El Nino to the other, but that is certainly something that we have seen. Northern parts of the southeast here in northern Georgia and northern Alabama is less certain. There's a lot more variability because that really depends on the strength of El Nino. And if you look at the opposite phase, La Nina, those years tend to be years that are fairly dry in winter. So La Nina is something that we have to watch for because we want to have good soil moisture going into the spring for planting crops and so on. Usually when you have El Nino, that's not an issue. The impacts of El Nino and La Nina in the southeast are summarized here. El Nino winters tend to be wetter and cooler than normal because of the subtropical jet that's pushing storms through the southeast, and we've certainly seen that this year. El Nino summers tend to have not very active Atlantic hurricane seasons. That's because that subtropical jet kind of blows the top off of any developing storms and keeps them from getting really strong. In winters, La Nina tends to be warmer and drier because all the storm activity has moved to the north. La Nina summers tend to have more active hurricane seasons. And so that is something that we'll be watching for in the coming. La Nina summers also tend to be pretty dry in the southeast, except where you have tropical storms that hit. And so that's something we'll have to keep an eye on. Right now we are in a strong El Nino, and because of that, we're having all these impacts of rain. What's really unusual about the El Nino this year is the warm temperatures, because that is not usually what you see in an El Nino winter. And so that's kind of an anomaly this year that's been very curious. And so that's something that climatologists are certainly going to be looking at. We know that in the strong El Nino, if we compare that to past El Ninos, 5 out of the last 6 strong El Ninos that we've had were followed by a La Nina. And so there's a very high probability that next summer we're going to be going into a La Nina, which suggests to me that probably next summer we're going to likely see the development of drought in some parts of the southeast. We'll probably go into the growing season with good moisture. In fact, there may be so much moisture that it will be hard to get into the fields. But later in the summer, I expect to see more dry conditions. It could be fairly hot because there won't be development of daily thunderstorms. And it really depends on tropical storm activity. We'll probably see more tropical storms than we have the last few years. So it's going to be really hit or miss whether they affect your area. You can see here's the strength of the El Nino. It's not the strongest one on record, but it's way up there. And so that's something that's very interesting. It's really helped this year by unusually warm water in the northern part of the Pacific Ocean as well as along the equator, which is something we don't see in every El Nino. Waiting for my arrows to come back down. There we go. All right, so the last part of my talk, I want to talk about now looking farther ahead down the way. And, looking at trends is hard because trends only reflect what's going on with current climate. When you're making drastic changes to the atmosphere, either with land use or with the atmospheric composition, then it's a lot harder to use past trends. So climatologists use climate models to try to figure out what's going on. Now, some of you may say, oh, well, I know what weather models are like, and they can't even get the weather right a few days ahead. It turns out that they're really built in different ways. It's kind of like comparing a Ferrari, which is more like a weather model, to a Dodge truck, which is more like a climate model. They're designed to do different things. They work kind of the same way, but the weather models are designed to get things done very fast because you want to have your forecast before you actually go out in the weather, whereas climate models are designed to really handle long-haul, different kind of conditions. So there's a whole different kind of set of different climate models that are used. Some of them are listed here on the lower right-hand side. A box model is very simple. Kind of works like a checkbook register. You keep track of the energy that's coming in, the energy that's going out, and then kind of see what the balance is like. Very simple model. Obviously doesn't include a lot of things like feedbacks from clouds or ocean temperatures or anything like that. The next step is the atmosphere-only model. You can have one that's got an ocean in it but no ocean currents. And then the ones that are probably the most realistic are the ones that are the full atmosphere, ocean, global circulation models, where they can vary all this different stuff at the same time and see how they all interact together. So over time, as computers have improved quite a bit, the models have also improved. If you go back to the mid-1970s, running all on the supercomputers of the time, which were, of course, now less powerful than the cell phones you've got, but they were the best they had at the time. Had some very simple rain parameterizations, had the sun, had a little bit of carbon dioxide, and not a whole lot else. And as the computers have gotten better and we've understood the land systems better, they've started to add things like land surface and ice and clouds. They've started to add an ocean. And now as you go on, they've started to add chemistry changes where you can actually see changes in the atmosphere due to the plants that are breathing carbon dioxide and oxygen. You can see circulation in the ocean. You can see the effects of volcanoes and the effects of pollutants. And all that together gives you a better picture of what's going on. And the computer models now run on just amazing computers, probably the biggest computers in the world. They use the same kind of computers that the defense uses. They're really, to capture all the intensity of what's going on in the climate requires a lot of computing power. The advantage to using models is that they can separate out the carbon dioxide effects. You can actually turn on and off individual things. You can turn on and off the ice. You can turn on and off volcanoes, or you can vary the sunlight a little bit and see what happens. And when you do that, and you separate out the impacts of just the natural forcings, which is mostly volcanic aerosols and solar variations, which are pretty small, but there's some there. And then you do a model simulation of what the temperature should have been over time. You see this kind of blue curve where you have a little bit of an increase, kind of maximized in the 40s, maybe around 50. And since that time, based only on the natural variabilities, we would have expected cooling. And instead, when you include the effects of carbon dioxide and sulfur dioxide and other anthropogenic changes, you see that the temperature goes up quite a bit. So the advantage of using the models is that you can really look at how those changes have occurred over time and sort of tease out what different factors are causing it. In fact, if you really want to go into here on the bottom right, I've just shown different sources of carbon. You can actually turn off carbon that's just emitted from petroleum or carbon that's just emitted from coal and things like that. And you can see what would happen if we changed our mix of energy blends in the US. How would that impact the climate? And so models are really good at being able to do that and separating all those different effects out. If we use those models, we can start to do predictions of future temperature. And this shows the 3-panel, which is kind of old now, but I like it because it kind of shows the range of variability. On the left-hand panel, it shows the observed 20th century trends. You can see the warming hole here. This is for temperature. Most of the rest of the southeast shows an increase in temperature. And here's just two example models, the Canadian model in the middle here, and the Hadley model, which is a European model on the right-hand side, kind of showing you the variability of what they predict the future temperatures to be. This is based on 2100 AD. And what it shows is that every single model, without exception, this is, depending on which year they're using, somewhere between 20 and 80 different models, every single one of them shows we're going to have an increase in temperature of between 5 and 10 degrees Fahrenheit in the next 100 years. It's not entirely certain how much that's going to be, but we do know that with a very high degree of certainty that the temperatures will go up. And that has a number of different impacts. One of the things we're going to see is a longer growing season. I did some work looking at the warmest years in the southeast and how that affects growing season, and it works out to about a 1 week increase in the growing season for every 1 degree Fahrenheit change in temperature. So we can see, an extra month long in the growing season, or maybe even longer than that, which is good and bad because it can increase the plants that you want to grow, but it also increases pests and diseases. And so that's something to keep in mind. Also, the warmer temperatures are certainly going to increase evaporation and evapotranspiration. So if you don't have water, that's going to cause more stress on the plant. Here's the same kind of panel now for the precipitation. Here's the observed 20th century pattern. You see it's a lot messier than the temperature is. And in fact, the Canadian model and the Hadley model don't even agree on which direction we're going to go with rainfall. The Canadian model says we're going to get drier. The Hadley model says we're going to get wetter. They have different assumptions about how thunderstorms are formed and how much humidity there's going to be. And so it's not surprising there should be some differences there. But it means we have very low confidence in exactly what's going to happen. So in that case, we almost have to go back to the trends. We know that the trends indicate increased rainfall intensity, which means more thunderstorms with the longer dry spells in between. Very hard to predict precipitation changes by season. And we really don't know the effects of El Nino and hurricane frequency, which are really two of our strongest drivers of precipitation in the southeast. So we have to be prepared for drier conditions, but we could also get wetter conditions and flooding. And so that's going to be an issue if you're worried about, for example, erosion. All right. Here's just some predictions by season just to show you. This is for late in the century. It shows that in the southeast, some areas will probably get wetter in the winter, and many areas will get drier. Spring looks like almost everywhere is going to get drier. Summer certainly drier, and a lot of that has to do with the warmer temperatures plus the evaporation. Fall could be wetter. That's very similar to what we saw with the trend graphs earlier in the talk. So what changes can we expect overall? This is kind of a summary. Average temperatures are likely to increase in all seasons by about 5 to 10 degrees Fahrenheit over the next 100 years. It's something we're going to have to deal with. Of course, on top of that, there's going to be the variability. So there's going to be more heat spells. There still will be cold spells too. It's still weather. It's not going to go away. But overall, we're going to see these temperatures increase. Daytime versus nighttime temperatures will both increase, but not necessarily at the same rate. A lot of that really has to do with humidity levels and the cloudiness, and that's a little harder to pick up in the models. We do expect to see increases in the maximum temperature and also warmer nights, which is an issue for animal health because heat stress really is exacerbated when you have animals that are not able to cool off at night. And the humans are the same way. So if you have people that aren't living in air-conditioned areas, then that could be a real issue if it doesn't cool off enough at night. Growing seasons, as I mentioned, will lengthen, and the rain will probably come in higher intensity bursts with longer dry spells in between. So those are the kind of things that we're going to have to plan for in the future. Some of the impacts that we'll see on plants, the warmer temperatures would increase the growing degree days, but also weeds and insect pests and diseases. Growing season's going to get longer, but we have to manage for a longer time period too. The increases in the extremes of temperature could lead to more fires. This is really important for people who are managing forests. If forest fires are going to increase, then you're going to have to be able to deal with that in terms of manpower and figuring out what to do with those burned areas. Winter storms could also change. We might get more ice storms instead of snow, and that probably would cause more damage to trees as well as infrastructure. And so that's something that would have to be considered in the future. The warmer temperatures, as I mentioned, would increase the evaporation from the soil. That's going to be a problem for big reservoirs, because if there's a lot of evaporation, that removes some of the water that would be available for human consumption. And we really don't know what's going to happen with hurricanes. If the warmer waters could increase the number of hurricanes, or they could increase the intensity. That's going to cause damage to southern forests and other infrastructure as well. And then the impacts of changing climate on animals, the increased number of days with extremely high temperatures will increase the heat stress. Well, actually reduce costs in the winter because you won't have to heat as much, although, in most areas of the southeast, that's not much of an issue right now. The increases in heavy rainfall may also affect things like manure storage in lagoons. You might have to plan to have enough freeboard so that you can have one of these big storms come over and not have overflowing. Or as far as the impacts on water, uncertainty of rainfall predictions makes it really hard to predict what's going to happen in the future. But we need to be able to store it in case there's those long dry spells. And at the same time, this higher intensity rainfall is going to increase erosion, and so that will be something that will also have to be considered in the future. The longer dry spells will probably increase the amount of drought, no matter what happens to the precipitation, because those temperatures are going to be so warm, they're just going to evaporate what falls from the sky. All right, so some of the strategies for adaptation that you can use are things like increase the water holding capacity of soils. Now, Steve talked about this a little bit in his opening. We want to be able to pull more carbon into the soils, but we also want to be able to make them more good sources of keeping the water in the soils. And one way to do that is by increasing the carbon. You can also do things like using cover crops to help lock that water into the soil a little bit better. Irrigation is going to be continuing to be important, and probably more important, but it's going to have to be smart irrigation. You're going to have to irrigate just areas that need it and put on just enough to get the plants through the dry spell. So we're not going to have that luxury of just being able to dump a lot of water onto it in the future. We're going to have to use it smartly. And other things we might be able to do are increase shelter for animals to reduce heat stress. They don't have to be really fancy things, but that could certainly be something that would help. And just in general, improve your resilience to extremes of climate. There's also some opportunities for things like taking advantage of the longer growing season. Bloomsbury Business Week had an article a couple months ago that talked about how the Southeast may be able to do more double or even triple cropping, and that could certainly help farmers that are looking for ways to increase their economic value of their crops. So as a sort of summary here, overall, what does the future hold? I think there's some challenges. The warmer temperatures are going to cause increases in diseases and pests. Certainly more stress on outdoor workers, especially at the hottest part of the day, more potential for drought, and there's going to be a cost to becoming more resilient for that. Of course, we can never tell about what the tastes of the human population are as far as what they want to eat. That's something that we really can't control, and it's not really dominated by climate. But at the same time, I think there's a lot of opportunities too. Population growth means that there is a potential for market growth there. Parts of the U.S. are going to see longer growing season and more rain. There are probably some parts of the south of the U.S. that will benefit from climate change, at least in the short haul. Obviously, we're not looking at just the U.S. because markets are international. Of course, we have a responsibility to people in other parts of the world too. So that's not the whole picture, but that's part of what we can see when we look at managing land. And smart management, use of water carefully, use of solar energies to cut down on use of diesel fuels and pumps and things like that can certainly be a factor. Also, there may be ways through carbon taxes or carbon capture in the future that producers may be able to benefit from some of the laws that are likely to change in the future. So I'm going to stop there and leave some time for questions. Here's my contact information if you want to get a hold of me. I do have a blog at extension.uga.edu where I talk about climate and agriculture in the Southeast, and you're certainly welcome if you haven't visited there to go there today.